Hello, I'm Mr. McChesney, and today we're doing a problem about orbital speed and period. The problem is, assume that a satellite orbits the Earth 225 kilometers above its surface. Given that the mass of the Earth is 5.97 times 10 to the 24th kilograms, and the radius of the Earth is 6.38 times 10 to the 6 meters, what are the satellite's orbital speed and period? And if you look to the right, you'll see a diagram of the problem. So whenever we start these problems, what we want to do is write out what we know. So the first thing that we know is that the height above the Earth's surface of the satellite is 225 kilometers. We also know, given us, that the mass of the Earth is equal to 5.97 times 10 to the 24th. And the unit for that would be kilograms, because it's a mass. We also were given that the radius of the Earth is 6.38 times 10 to the 6th meters. So as we look at this problem, I see two things. I see that I have meters and kilometers for my two units of distance. And whenever you're doing a problem, you want to make sure that you use the same units. You don't want different types of units. So I want to make sure that both units are the same, either both kilometers or both meters. And if we look back in our text, we'll see that we are usually using meters in our answers. So I want to change my height above the Earth's surface from kilometers to meters. And earlier, we saw how to do that using dimensional analysis. So I start out by writing my number, 225 kilometers. And to do dimensional analysis, I draw a line, and I'm going to get rid of my units kilometers, which go on the bottom, and I want to get into the units meters. And I know that 1 kilometer is equal to 1,000 meters. And one way to write 1,000 is to write it as 10 to the 3rd meters. If I do that, I got kilometers divided by kilometers, so those units cancel out, and I'll be left with an answer in meters, because that's the only unit I have left. So this equals, my height equals 225 times 10 to the 3rd, and then we divide by 1, which keeps it the same, and my unit would be meters. Now as I look at that number doesn't look like scientific notation. It's close, but it's not quite right. The simple part, this first number here, has to be between 1 and 9.99, so I need to move the decimal place over. So I need to move my decimal place 2 spots. So it's in between the two 2's. When I do that, I get 2.25 times 10. Since I moved it 2 spots to the left, my exponent becomes larger by 2, so I get 10 to the 5th. And I still have the same unit, meters. So that's the height above the Earth. So now we can start the problem by looking into the chapter and seeing what formula we use. So as I scroll down here, the formula I'm going to use is orbital speed, v, is equal to the square root of big G, the universal gravitational constant, times the mass of the Earth, divided by r. And in this case, r means the radius of the orbit. So that means from the center of the Earth all the way out to where it's orbiting And as you can see on the diagram, that would mean it'd be the radius of the Earth and the height above the Earth, those two numbers added together. So in order to find r, we need to add our two numbers together that we have given to us in the problem. The height above the Earth that the satellite is moving around the Earth, plus how far from the center of the Earth is it, the radius of the Earth. So if I add those two numbers together, I'm going to get the height above the Earth, which was 2.25 times 10 to the 5th meters, and here's why we need to have both units being the same, plus the radius of the Earth, 6.38 times 10 to the 6th meters. Now as I look at those, I have different exponents. I've got a 5 and a 6, and when you add these, you can use your calculator and just add them and it will give you a correct answer. It may give you a few extra digits because calculators don't do significant figures very well, but sometimes your calculators don't work. Batteries run out, you forgot your calculator, so an easy way to do this to try and help you out is you want to get both exponents to be the same. So I'm going to take this 2.25 number, I'm going to move the decimal place 1 to the left, which is going to make my exponent from a 5 to a 6. And then it's just simple addition. I add the simple parts, 0.225, and I add that to 6.38, and then I keep the exponent the same. So I'm going to get radius of the orbit is going to be 6.61 times 10, keep the exponent the same, 10 to the 6th meters. Now I've rounded off here because I have 3 significant figures or significant digits in the first number, and I've got 3 in the second number, so my final answer should have 3. So now I'm going to scroll down to a fresh screen and show you the rest of the problem. Okay, so now we're ready to solve the problem. We have all the numbers we need. So we start out, we're going to look for our orbital speed. So orbital speed is v times the square root, and we had big G, which is 6.67 times 10 to the negative 11th, and we want to write our units here, even though there are a lot of them. Newtons times meters squared divided by kilograms squared. And I'll show you later why it's useful to keep track of your units. So that's the first number, that's big G. And we'll multiply that by the mass of the Earth, 5.97 times 10 to the 24th kilograms. Just going to extend my radical a little farther. So I've got big G times the mass of the Earth, and I'm going to divide all of that by the radius of the orbit, which is both the height above the Earth plus the radius of the Earth. So that's 6.61 times 10 to the 6 meters. And you want to be careful here when you type this number into your calculator. It's probably a good idea to use parentheses because your graphing calculator sometimes won't read this as one whole number, and you'll end up with a different answer. And this is another way I'm going to show you how to check your work. Alright, so we've got all our numbers. We're going to multiply the top together and divide by the bottom. And one thing we can check here is our exponents. So to know if I'm doing this correctly, if I look at my exponents, I've got 10 to the negative 11th power, and when I multiply exponents, I've got 10 to the negative 24th, so I got negative 11 here, to the 24th power here, and to the 6th power here. when you multiply, you add the exponents, so negative 11 plus 24. And when you divide, you subtract an exponent, so minus 6. So if I do that, I get negative 11 plus 24 gives me 13, minus 6 gives me 7. So I should end up with a number that's 10 to the 7th power. But since I'm square rooting it, you end up dividing by 2. So I should get an answer that is something either 10 to the 3rd or 10 to the 4th power. And this is where, if your calculator is a graphing calculator and you didn't use these parentheses, and you come up with an answer that is 10 to the 13th, 10 to the 6th power, or something along those lines, that's a good idea to check that to make sure that everything worked the way it's supposed to. So my answer, if I multiply everything together, I get my orbital speed is equal to 7.76 times 10 to the 3rd, and my units for this would come out, if I look at them, I've got a couple things. We know speed should be meters per second. And if I kept track of my units, I can check to make sure that's correct. So if I look, I've got a Newton times a meter squared divided by a kilogram squared times a kilogram, and then that's divided by a meter. So I've got some units that are the same, so I can say, okay, I've got a meter on top and a meter on bottom. My meter squared, if I divide it by a meter, will give me meters. And I've got kilogram divided by kilogram squared, so I can get rid of one of the kilogram squared parts. So that leaves me with a Newton times a meter over a kilogram. As we look at this, this doesn't look like meters per second. But if we remember what newtons are, a Newton is equal to a mass times an acceleration, which would be kilograms times meters per second squared. And I had meter and kilogram left over, so I take this kilogram meter per second squared. If I put it in for my Newton, here's what I get. I get a kilogram times a meter divided by a second squared times a meter divided by a kilogram. So I see I've got kilograms and kilograms, one above a fraction, one below. Those cancel out. And a meter times a meter gives me a meter squared divided by a second squared. And you may say, well, that doesn't look like meters per second yet. But remember, we square rooted our number, and when you square root it, you divide the exponents by 2, so 2 divided by 2 is 1, 2 divided by 2 is 1, that leaves us with meter per second. So we get this answer of orbital speed is equal to 7.76 times 10 to the 3rd. My units are meter per second. That works with all the units we've got. I've got a power times 10 to the 3rd. Checking my exponents, that gives me a reasonable answer. So that should be the correct answer, 7.76 times 10 to the 3rd meters per second. Okay, now we've answered the first question. The second question was, what's the orbital period? So if we look, we've got an equation in your book that is T equals 2 pi times the square root of the radius of the orbit cubed divided by the universal gravitational constant, big G, times the mass of the Earth. And this problem is going to be very important in your graphing calculators if you're using them, to put parentheses around those two numbers when you multiply them together. So if I start plugging in the numbers we have from earlier in the problem, we've got 2 pi. And I would suggest if you're using a graphing calculator, use the pi button on your calculator. And it's going to be times the square root of my radius of orbit, which is the radius of the Earth, plus how high above the Earth the satellite is orbiting. So that's 6.61 times 10 to the 6 meters. And I'm going to cube that number. And that's going to be divided by the universal gravitational constant, 6.67, times 10 to the negative 11th, and that's going to be newtons times meters squared divided by a kilogram squared. And I'm going to multiply that by the mass of the Earth, 5.97 times 10 to the 24th. Let me erase that there. Times 10 to the 24th kilograms. So I'm just going to extend some lines here, extend my radical. And again, you want to use parentheses when you do this in your graphing calculator. So when you do all those numbers together, you get an answer that should be 5.35 times 10 to the third seconds. You should check your exponents again just to make sure everything's correct. Check to make sure your units cancel out. And that will give you the final answer.